Hello there. Welcome to my YouTube channel. In this video, we will be learning about linear non-homogeneous equation and how to solve these equations. So a first order differential equation takes in the form of a1 to the function of x dy dx plus a0 to the function of x times y is equals to g of x is said to be linear in the dependent variable y. So we take in the form of just dividing this a1 to the function of x. Then we notice that this is the resulting equation. What's left here is dy dx. That one, a to the 0 to the function of x divided by a1 to the function of x will have p as a function of x, and what's left is y here. Okay, this one, a0 to the function of x divided by a1 to the function of x takes in the form of p to the function of x, and also g to the function of x divided by a1 to the function of x takes in the form of this one. If we divide that, so we have to the function f to the function of x. Okay. We take note. Let's erase this one. Okay. We take note that if we say that f of x or g of x is equals to 0, so this takes in the form of a homogeneous equation whereby you can really solve this by what we call separation of variables. Okay, remember that dy is equals to negative a to the o to the function of x over a1 to the function of x. Okay, now in homogeneous equation there are different approaches on how for you to calculate the solution to a problem. So solving a linear first order differential equation, put a linear equation of the form 1. What do you mean by that is the equation 1 was first established dy dx, okay, that was a while ago, plus a sub o to the function of x, y is equals to g of x. This is your equation 1 into the standard form of dy dx plus p to the function of x, y is equals to f of x. Okay, this is the standard form, just what we did in the last slide. Okay, from the standard form, identify the p to the function of x and then find an integrating factor e to the power of p x dx, or we introduce this one, the phi, as the integrating factor of integral of p to the x dx. Remember, your px is here. You got that from here and you substitute that here. Multiply the standard form of the equation by the integrating factor, and the left-hand side of the equation is automatically derived from the integrating factor of y. Integrate both sides of this equation, and your final equation will be this one, y to the function of x is just equal to the phi inverse of that multiplied by integral of, okay, f of x here times the integrating factor phi, okay, plus c and close parenthesis. So we'll have two examples here. So now, solving a non-homogeneous linear differential equation in example 1, say solve dy dx minus 3y is equals to 6. As you can see, it is in its standard form already. So no need to do the uh, step 1 of the equation, of the solution. So what is your p? Your p to the function of x is just equals to negative 3. Those your integrating factor phi is equal to negative 3 dx, such that e negative 3 dx or e negative 3x is your integrating factor. Then you do the format or the formula y to the function of x is equals to, okay, what's again the equation? Phi negative 1 multiplied by integral of f of x multiplied by phi plus c. We take note that the f of x here is this one, the 6. Okay, substituting e negative 3x, and that we have negative 1 multiplied by, okay, uh, we took away, we took outside the constant, so we have dx here multiplied by e to the negative 3x plus c. So this takes in the equation equal to e 3x, then 6, and then we have, okay, eu du. So you have negative 3, okay, integral of, no, I mean negative 3 multiplied with the integral of e, okay, e negative 3x, okay, plus c. Yeah, okay. So this takes in the form of e 3x negative 2 e negative 3x plus c. Those multiplying distributing is equals to negative 2 plus c e 3x. This is your general equation. So in the next page, in the next slide, we will solve another problem. So solving a non-homogeneous linear equation. In this case, we have the electrical circuit, inductance di dt plus R resistance times I is equals to E, and it is to solve at a particular solution. I to the function of time equal to 0 is equals to I to the 0. And we take note that L, R, E, and I to the sub O are constants. So the first we need to do is to transform this equation into the standard form. This means that we have to divide all of these by L. This becomes di dt plus R over L I is equals to E over L. Okay, we take note. R and L are constant, so anything constant divided by constant is constant. So we name this as, say, A, and E is constant divided by constant. So we make this as B, which is constant. So this takes in the form of di over dt plus AI is equals to B. And we take note that P to the X is A. Remember the standard form, dy over dx plus P to the function of X times Y is equals to F to the function of X. So dy dt is just in similar form of dy dx. A to the x, a to the function, a to the a multiplied by y. The a here is a function of p to the function of x. The I here is represented by y. And the b here is a constant which is represented by the function of x. So therefore, your integrating factor phi is equals to E integral of A, okay, dt. Since we are talking of dt here. So therefore AT. Those your equation becomes, this means di or I to the function of time is just equal to phi negative 1 multiplied by integral of f of t, okay, function of time multiplied by phi plus c. So what is your e to the your integrating factor? E to the negative 80 okay, a negative 80 your f of x is b, but b is constant, so we take that out to the function of a et dt plus c. Okay, so that means we have e negative 80 b a to t, okay, over a plus c. Okay, so we multiply that, we distribute b to the a plus c e to the negative at. However, as part, and if we remember that we have A is equals to R over L, take note that B is equal to E to the L, this one. A is equals to R over L, and we substitute that. So we have E to the L divided by R to the L plus C E negative AT. So this becomes, we cancel the L. We have the E to the R plus C equal to C AT. This is your general equation. Okay. Oops, we gone too far on this side. So to find the particular equation at I to the 0 is equals to I to the O, which is I to the O is constant, is equal to E over R plus C E negative A uh, multiplied by 0. A to the 0, A to the 0 is, A to multiplied by 0 is 0. E to the 0 is 1. So therefore your constant is equals to I to the O minus E R. Therefore your particular solution becomes I to the function of time is equal to E over R, okay, plus C multiplied by O or I to the subscript of 0 over R. Okay, this is your particular solution given the initial value problem of here. So hope you learned, and thank you for your time.